Okay, so I'm going to be doing a solution for number 9 on today's assignment. This is the second half of the worksheet. I assigned 1 through 7 yesterday, so this is 8 through 11. And remember, you don't have to do 12, but this is number 9. So it's a 70 kilogram box, slides down a 25-degree ramp. Okay, so let's just start with an image here of what's happening. Here we have the box, and we'll just say that's 75. Actually, you know what? I'm not gonna do. I'm not gonna put the mass in there. I want to save that for some vectors. It's 25 degrees. So I'll just put it up here. M equals 75 kilograms, and it has an acceleration. It's actually moving down here at 3.60 meters per second squared, and that is your acceleration down the ramp. Okay. So it's asking, A, what is the mu sub k between the box and the ramp? So our question is mu sub k equals what? And what would be the acceleration if it's 175 kilograms? What? Okay. So the first thing we're going to do here is take a look at the forces that are acting on this box. So we have the force of gravity going down, and that's mg. We have the normal force going like this, and I'm going to, again, as I showed in the previous video, I'm going to extend that vector down this way, keeping it the same size and the same orientation. So this is going to be my F sub n. And then here we can see that this part of the triangle pointed down the ramp, parallel to the motion, is called force parallel. All right, so these are the three forces sort of acting on the box right here. Now, there is another force I want to point out real quickly, and I'll make it a little bit thicker here, that there's a frictional force that opposes the slide down the ramp. So we'll call this F sub F. So we really have four force vectors acting on this object. And A says, what is the mu sub k between the box and the ramp? So let's start. The first thing we're going to start with is, okay, this is A, is this idea that F net equals ma. So what are the net forces? Remember that the net force means total force, and since this box is sliding down the ramp, we only want to concern ourselves with forces that go either up the ramp or down the ramp. So there are only two forces directly that go down the ramp or up the ramp, and those are those two forces. Right? So those are the two forces that will be the net forces. You know, if there's a kid pushing or pulling or some other force going up or down the ramp, we would include that, but there's really just F parallel and the force of friction. Again, those are the only two that align up or down the ramp. So the F net, in this case, is going to be, and I'm going to call downward positive for my reference frame because the object's going down. So I'm just going to call downward positive and anything up being negative. That means that F parallel is going to be a positive force and the frictional force is a negative force. Okay. So the net force is really just F parallel minus, or you could say plus a negative force of friction if you want. And the OCD a little bit in me is going to say, nope, I don't like those brackets. So let's just forget about those brackets. And in fact, notice how plus and minus, I'm just going to save myself a little bit of space. Let's call that minus. All right, and the OCD gods are happy, and my world makes sense again. All right, it's nice and pretty. So F parallel minus the force of friction, that will result in the MA of the box down the ramp. Now, force parallel, we already know from our equations that, remember that F parallel is equal to mg sine theta. Remember that the normal force was mg cos theta, and then the gravitational force is just mg. That was from a previous video, but I'm just going to use those. I mean, this is an important idea for this problem. So the F parallel is mg sine theta. The force of friction It looks like somebody just played a chess move. Bishop takes d5. I hope that was a bad move because I want to win this game. Anyways, the force of friction is always mu sub mu times the normal force. So I'm going to use that formula right here. It's going to be mu sub k times the normal force. And that's all equal to ma. So the point for this problem is we're trying to figure out what mu sub k is. So we can just separate, or we can just solve algebraically for mu sub k, and we can just do that right now. So I'm going to bring this whole term over to this side, and I'm going to bring this whole term over to the other side. And what it's going to look like when I'm all said and done is it's going to look like mg sine theta minus ma equals mu sub k times the normal force. And guess what I'm gonna do? I'm gonna divide both sides by the normal force. That brings it over there. And remember that the normal force, whoop, is really just mg cos theta. So I'm just gonna go ahead and replace that right now with mg cos theta. Alrighty, so we could plug this in if we want to, but we notice that there's a common variable in all three terms, and that is m. So the mass is going to cancel, and this is an important part for part B in a moment. The mass totally cancels. So the mass is irrelevant to the motion down the ramp. The mass cancels. So it's g sine theta minus a all over g cos theta, and that will get you your mu sub k. I'm not going to spend time calculating this on my calculator, but I will set it up for you. That means that 9.8 times the sine of 25 minus 3.60 all over 9.8 times the cos of 25, whatever all that nonsense is going to be your answer there. All right. Now for part, well, that's the answer for A. For part B, what acceleration would a 175 kilogram box have? Okay, so all they're saying is what if you change the mass? Well, we've just discovered that the mass is irrelevant. It could weigh 175 trillion tons for all we care. The acceleration is not going to change, and the mu is not going to change. So what would the acceleration be? Well, it's still going to be, so I guess I'll have to do it this way. It's still going to be 3.60 meters per second squared. Again, the mass is totally irrelevant because it cancels out. And you're going to discover that a lot when we do this unit with forces, is that a lot of times, in fact, most times, the mass of objects is totally irrelevant to their accelerations and things like friction. It's really an interesting phenomenon. Anyways, that is the video for 9.